In this presentation, we're going to talk about parallelizing binary searches. But before we even do that, let's just get some background so we kind of understand where we're headed. We'll write some code shortly, but we need to set the foundation for that code so you really understand it. So binary searches always act on sorted arrays. The binary search algorithm searches for a match in a sorted array. But before we even talk about binary searches, let's talk about linear searches. Here you have a list of numbers. I believe there are 15 numbers here. And notice that they are in order. They're sorted. Okay, 1, 2, 4, 5, 7. They're not necessarily sequential, but they are at least sorted. No duplicates, and they're all sorted. Okay, so we have a red arrow here, and we're going to start searching at index 0. Let's say we're going to look for 31. So that's not it, so we got to go up. We see 2 here, that's not it, so we got to continue. That's 4. That's not it. Remember, we're looking for 31. 5 is not 31. 7 is not 31. 10, and so forth. So we actually have to traverse the entire list. Finally, we get to 31, and we found what we're looking for. So potentially, in the worst case, we could have to search the whole list before we finally found the number that we're looking for. So that's a linear search. But there's actually a better way to do it, and it's called a binary search. It's similar to a guessing game. Remember how when you learned how to play guessing games, someone said pick a number from 1 to 20? And you always knew you need to start right in the middle. So you'd say 10. And then they say, well, that's too high or too low. And so from 10, if it was too low, you'd go halfway between 10 and 20, 15. Okay, and if that was too high, you'd go halfway between 15 and 10, right? The last one you were at. So you might say 12 or 13, let's say for argument's sake, it's 13, and maybe that's it. So as you can see, you actually have to search fewer positions by using a binary search than using a linear search. I mean, the exception to that would be if it was the very first thing you searched for. Okay, so here we have the same list. The same list as we had before, the 15 sorted numbers. So we're going to start in the middle, which is 15. Okay, 15 is lower than 31, so we somehow need to move up. We're not going to move up 1, though. We're going to split the difference between 15 and the last number we looked at. Well, since we didn't look at anything else, it's going to be all the way at the top. So we split the difference between 15 and 42. Actually, we split the difference between 15 and the end of the list. Okay, so we split the difference and we go to 25. Okay, so 25. Notice the blue arrow here. We left it there so we could remember where the last point we checked, because we don't want to go too far and back up below 15. We don't want to ever go below 15. Okay, so that's too low. Now we're going to split the difference again, go up. 34. Notice we've marked where we were at, so we don't ever want to go below 25. Okay, now we're too high, so we got to go low. And 31. That's the number we're looking for. Notice we marked 34, so we would never go above 34. So we did 1, 2, 3, 4 comparisons, and on the 4th one we found it. Whereas before, when we were going up when we were doing the linear search, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It was on the 12th comparison that we found it. So as you can see, the binary search is much faster. So there's this thing in computer science called complexity. Algorithms have what's known as asymptotic complexity. It gives you a theoretical idea of how that algorithm will perform. So a linear search has a complexity known as n, and n stands for the number of items in the list. However, a binary search has the complexity known as log n, which is much faster than n, especially for large data sets. But now, if we can actually parallelize a binary search, we'll get even better performance. So let's take a look at some code. So here I've got a program that does a linear search. First, I create a lot of entries in a data array. Then I just arbitrarily chose a search number. I record the starting time, I loop through and I look for the number. This is linear search, remember. Calculate the elapsed time, and then I go ahead and show the elapsed time. Okay, going to run this thing and see what kind of results we get. Oops, it's off the screen, but so elapsed time of 156 milliseconds, which isn't very much. Now I actually had to make this array really large in order to even get that, because a small array it's going to be 0. This is just a really fast search anyway. Okay, so I've converted that program so that instead of a linear search, it uses a binary search. And I need to know the middle of the array. So search index is array size divided by 2. And here I'm going to record my low water mark and my high water mark. Remember, once we have a low water mark, we never want to go less than that because we're wasting time. Once we have a high water mark, we never want to go above that because we're wasting time again. We record the time. This is almost identical to what we did in the linear search, but this time instead of indexing I, we're going to index search index. Okay, now we do our comparison. We say, okay, is this number where we're at lower than the search number? If it is, first we record the low water mark. We find the delta between high and where we currently are, and we actually don't want the entire delta. We only want half of it. So we just add half of it to the search index for the next go around. Otherwise, if we're too high, we want to move left, but we remember our high water mark. We find the delta, and instead of adding half the delta, we subtract half the delta, and we do it again. So let's see what kind of performance we get out of this, what kind of a difference in performance we get. Move this over here. So it said 0. It's probably not 0 milliseconds because the clock where the millisecond timer comes from has a granularity error. So I would guess it's somewhere low. But remember, we had 156 milliseconds before. Now we're down close to 0. So a huge performance gain. Now if we can just parallelize this, it would be even better. So in order to parallelize this, what I did was I broke up the array into 4 blocks. Okay, 1, 2, 3, 4. And I did a binary search on each of the 4 blocks. So I wrote a function called doBinarySearch, and it just gives it where the block size starts, where the block size ends, in other words, start, end, and gives it the search number. Okay. So the doBinarySearch is the same code as we saw before, almost identical. The only thing is low watermark is going to be the start -1, and high watermark is n+1. So we want to sort of push it one more. So it's inclusive. It's inside the high and low watermarks. Same thing here. Now it does set this variable found to 1 so that the other threads know when to bail out. It returns. This code is the exact same. And here, if found doesn't equal 0, that means one of the other threads found it, so I can bail out. So in conclusion, a lot of algorithms benefit from optimizations, and the example I gave was going from a linear search to a binary search. Very clear optimization there. In addition, many algorithms benefit parallelizing them, and I showed you how to parallelize the binary search. And the last thing I want to say is OpenMP makes this stuff really easy. So here's your call to action. Crack open the OpenMP documentation and learn how to do it.